As naturally fair as Hamilton's method seems, it does have many shortcomings, and we're going to see three of the big ones here. So the first one we'll see through this table right here. So we have states A, B, and C, and we have that there's 100 seats to be allocated among the different states, and we see that the sum of the populations is going to be 10,000. And with that information, we can fill in the rest of the table, so we can find the standard quotas. And just as a review, how do we find the standard quota, for example, for state A? Well, it's going to be done by taking the sum of the population, so it's going to be 10,000, and then we need to divide that by the number of seats, so it's going to be 100, so that's our standard divisor. That means every seat is 100 people. So since A has 360 people, it should get 3.6 seats if we can give fractional seats. And same thing for the other people, other states. But of course we can't give fractional seats. So using Hamilton's method, we go with the lower quota. So we go with 3, we go with 54. There's no decimal here, notice that. And we go with 42. And that adds up to 99, which means there's one seat left. And we give it to the person, we give it to the state with the highest residue. And in this case, that's 0.6. which is the highest residue. The residue here is 0, and the residue here is 0.4. So the seat goes to state A, and A gets 4 seats, and the other two states get as many as they had in the initial handing out of seats. So now let's note something really fast before we see why we're going to find a paradox here. Note that this 0.6, this residue right here, is going to be 16.7%. It's going to represent 16.7% of the population of A. This residue here, which was 0, represents 0% of the population of B. And this residue here, 0.4, represents less than 1% of the population of C. So in this case, even though it is kind of by luck, it's a very good thing that A got the extra seat, because they're the ones who needed it the most. They're the ones who the residue counted for most of their population. So this is good. But now here's where things start to get bad. What if we increase the seats to 101? So remember, the amount of seats is arbitrary. It can be really anything. So what if instead of 100, it were 101, just one more? So something would change. The standard divisor would change, because we'd have to take this 10,000 and divide it by a bigger number. Therefore, the standard divisor would be now smaller. Okay, so it would be 99.01. And if we calculate all of these all over again, so A, the quota is not 3.6 anymore, it's 3.64. B, it's now 54.54, and C, it's 42.82. Okay, so now what changes? So the lower quotas are the same. It's still 3, 54, and 42. But the order of the surplus is no longer the same. Since 0.82 is now the biggest residue right here, this first place goes away and goes over here. And in fact, these two don't get anything. So then the final is going to be different too. This final will be 3. This 54 will not change, and this, instead of a 42, this state C got another extra seat, so it's going to be 43. So now things have changed. Now this is a weird paradox. This is called the Alabama paradox, after a time in history when this happened, dealing with the state of Alabama. But here's why this is going against our gut feeling. Our gut feeling should say that if you increase the number of seats even by 1, then it shouldn't cause any states to lose seats. It should just cause some certain states to gain a seat, for example. So the fact that it does cause states to lose seats, in fact, it causes A, our smallest state, to lose a whole seat. And that's kind of devastating for state A, because state A, having only 360 people, losing one seat is a really big deal. It's like losing a lot of representation in your population. So our gut tells us that by increasing the number of seats, you're just going to be adding seats to people, not taking seats away from anyone. But under Hamilton's method, it is very possible for especially small states to lose seats. So that's one bad thing. Now the next thing is called the new states paradox. And the name suggests that we're adding new states. So look at this first table. So I'll draw a line where the second table begins. So before this line, look at this first table. This is simple. We only have two states, A and B. We have the populations, the number of seats is 100, and we calculate the whole table. So let's just see what happened in general. We had the lower quota here as 10, lower quota was 89, and since 0.55 is higher than 0.45, state B got the extra seat, and they went up to 90. Okay, so now before we look at the other part of the table, let's make a little guess. So what's going to happen in the next part of the table is we're going to introduce a new state, C. And because there's a new state, we need more seats. So we're going to boost the number of seats from 100 to 105. So what do we think is going to happen? What we think should happen is those 5 new seats should go to C and nothing else should change, right? Adding a new state shouldn't change the representation of, or the proportions between these other two states. So nothing should change between A and B. But in fact, under Hamilton's method, it does. So this small table here captures all the new information. So we have states A and B, and their populations are going to be the same. State C is new, with a population of 5,310 people, and the quotas are here. It's going to be 10.42, it's going to be 89.29, and the new quota is 5.3. So taking the lower quotas, we have 10, 89, and 5. So notice these two lower quotas are the same, and this is 5. So the 5 seats that we added are in fact going to C. That's good. That's what we wanted. But now what's happening here? Now we have 1 seat left over because these lower quotas add to 1 of 4, and we have 1 seat left over. So who gets it? Well, in the previous case, the highest residue was for B, but now the highest residue turns out to be for A with 0.42, which is higher than 0.29 and 0.3. So that means A gets the new C, A gets 11, B is 89, and C is 5. So look at what happened. A was 10, but now A is 11. B was 90, and B is now 89. So by adding a new state, which should really have no effect on the other two states, we have actually changed the proportion of seats between A and B. And this is called the new states paradox. It's another shortcoming of Hamilton's method. The last shortcoming we'll look at with some lined paper here. So this is called the population paradox, and we'll start by looking at this table here. So this is a new allocation table, and we have 24 seats. We have 3 states, A, B, C. Here's their populations. Here's the total, and I've filled out everything. So we have the standard quotas, lower, surplus, final. Now let's look at a new table, and let's look at them side by side, in fact. So we have the same states, A, B, C, and let's pretend after the course of a year, 2 years, however much time, their populations increased. So A's population increased by 28%, B's increased by 27%, and C's increased by 16%. So obviously now the population is higher. We're going to have to recalculate some things. So the number of seats has stayed the same. It's still 24. So before we look at the rest of the table, let's make a little guess what we think should happen according to our gut. Well, what we think should happen, since A's population rose the most, then they should get the most increase of seats. Or at least, they should not lose any seats. That would be really weird, because how can a state's population increased and have them lose seats? That means that they had more people, but they're getting less representation. That really makes no sense. But it turns out, again, under Hamilton's method, this is something that can happen, and it will happen in this example. So let's look at these two tables side by side again. So we have A, we have the new populations, we have the new standard quotas here, and we take the lower bounds. The lower bounds are actually not the same, because we had lower bounds here 3, 6, 14. Now we have 3, 6, 13. So now we have 22. And whereas before we had 1 seat left over, now we have 2. So we're going to go ahead and give it to the highest residues, which is 0.77 and 0.64, which means that in the end, A got 3, B got 7, and C got 14. But wait a second, what was the numbers in the previous example? A got 4. That's a 4. So B got 6 and C got 14. So it turns out that A, whose population went up the most by 28%, actually lost representation, and that really makes no sense at all. So these three are all shortcomings of Hamilton's method, and they all stem from kind of the same place. It's the fact that these residues are unpredictable. They don't really say much about the actual representation. They don't say whether a state needs it more or needs it less. The way the method works, it just favors whichever residue tends to be higher. And these residues can just change by the whim of adding more population or adding more seats. They're really unpredictable. And since they're unpredictable, the final outcome is unpredictable and often turns out to be disastrous. So we'll look at some stronger methods in the next few videos.